Deep in the cosmos, under conditions impossible on Earth, crushing pressures, extreme temperatures, insane densities, and perfect isolation, the universe forges materials that defy our understanding of physics and chemistry. These aren't just curiosities, they're glimpses into states of matter we can barely replicate in labs. Here are the 10 strangest materials that actually exist in space, counting down from number 10 to the most mind-bending at number 1. Metallic hydrogen in Jupiter's core. Deep within Jupiter, about 10,000 kilometers below the swirling cloud tops, hydrogen, the lightest element in the universe, undergoes a shocking transformation. Under pressures exceeding 4 million atmospheres and temperatures around 10,000 Kelvin, hydrogen atoms are crushed so tightly that their electrons break free and flow like a liquid metal, rivaling copper in conductivity. This is metallic hydrogen. Predicted in 1935 by Eugene Wigner and Hillard Huntington, it remained theoretical until NASA's Juno spacecraft arrived in 2016. By mapping the planet's gravitational and magnetic fields, 14 times stronger than Earth's, scientists confirmed a massive shell of metallic hydrogen, roughly 40,000 kilometers thick and comprising about 80% of Jupiter's mass. This vast ocean powers the planet's dynamo, generating its colossal magnetosphere and auroras 1,000 times brighter than Earth's northern lights. In 2017, Harvard researchers Isaac Silveira and Ranga Dias claimed to create it in a diamond anvil cell at 495 gigapascals. A fingernail-sized piece, stable at room temperature, could revolutionize rocketry with a specific impulse of 1,700 seconds, nearly 4 times better than the best chemical fuels. But the anvil failed catastrophically within hours. The sample vanished, and no lab has definitively replicated it. Jupiter guards its metallic heart jealously, a metal made from gas, forever beyond our easy reach. Quasicrystals from the Khatyrka Meteorite. In 2009, mineralogist Luca Bindi examined samples in a Florence museum and found something mathematics said was impossible: a meteorite fragment from Russia's remote Koryak Mountains with 5-fold rotational symmetry. Classical crystallography allows only 2, 3, 4, or 6-fold symmetry. 5-fold symmetry can't tile 3D space without gaps. Yet here it was, in perfect geometric precision via electron diffraction. Named icosahedrite, aluminum, copper, iron, it has long-range order without true periodicity, like a 3D Penrose tiling. In 2011, physicist Paul Steinhardt led an expedition to the Khatyrka site, recovering more samples dated to 4.56 billion years ago, formed in violent asteroid collisions at over 5 kilometers per second. This vindicated Dan Shechtman's 1982 discovery of quasicrystals in lab alloys. Linus Pauling famously scoffed, "There are no quasicrystals, only quasi-scientists." Shechtman faced fierce opposition, but won the 2011 Nobel in Chemistry. The Khatyrka Meteorite proves the universe creates what we deem impossible, forging mathematical anomalies in cosmic chaos while we debate their existence. Superfluid helium-3 in neutron star crusts. In 1972, at Cornell, Douglas Osheroff, David Lee, and Robert Richardson cooled helium-3 to 0.0025 K above absolute zero and watched it become a superfluid, zero viscosity, flowing up container walls, dripping through molecular pores, rotating forever without slowing. They won the 1996 Nobel for showing quantum effects on macroscopic scales. The universe has done this for billions of years, inside neutron stars, stellar corpses, where a teaspoon weighs as much as Mount Everest. At densities of 100 billion to 100 trillion grams per cubic centimeter in the inner crust, helium-3 and light elements form Bose-Einstein condensates and superfluids even at 100 million Kelvin. Anthony Leggett predicted this. Nobel 2003.
Evidence: pulsar glitches. The Vela pulsar, of 1,000 light-years away, is one of the universe's most stable clocks. Yet every 3 years it suddenly spins faster, rotation period dropping by 1 part per million in seconds. The superfluid interior rotates independently from the crust, building stress in quantum vortices, tornado-like structures. When vortices unpin, angular momentum transfers violently, making the star convulse. Quantum mechanics operates on kilometer-sized objects across light-years.
Carbyne chains in interstellar clouds. In the vast darkness between stars float perfectly straight chains of carbon atoms, the strongest material known, with tensile strength twice graphene's and stiffness several times diamonds. Theory predicts Carbyne withstands around 100 million newtons per square meter. On Earth, Carbyne is violently reactive, cross-linking into graphite or exploding with oxygen or water in milliseconds. Chemists struggled for decades to make even tiny amounts.
In 2016, Michael McCarthy's team at Harvard-Smithsonian used Green Bank Telescope and ALMA to detect long chains up to 13 atoms like cyanooctatetrane around IRC plus 10216, a dying carbon star 500 light-years away in Leo. Column densities suggest up to 10% of carbon in some regions exists as these linear chains. Space's near vacuum, 10 to 50 K, no reactive molecules, preserves them naturally. That same year, Rice University synthesized stable Carbyne in labs by capping ends with bulky groups, mimicking cosmic isolation. The universe casually produces what we can barely create, scattering the strongest substance through interstellar clouds, forever beyond harvest. Strange quark matter. In 1984, Edward Witten proposed that protons and neutrons aren't the most stable quark configuration. At densities over 500 trillion grams per cubic centimeter, in the cores of the heaviest neutron stars, quarks might form a soup of up, down, and strange quarks, strange quark matter, or quark-gluon plasma. Disturbingly, it might be more stable than ordinary nuclei, meaning our matter is metastable, like a ball on a hill. A single strangelet, microscopic droplet, touching normal matter could trigger a chain reaction. Nuclei convert, release energy, create more strange quarks, consuming everything, potentially a planet, into a dense quark sphere. Relic and LHC create quark-gluon plasma for 10 to the negative 23rd seconds, no strangelets found. Safety reviews in 1999 and 2008 say if conversion were easy, cosmic rays would have triggered it long ago. Yet neutron stars over 2 solar masses suggest exotic cores beyond neutron degeneracy. Strange quark matter remains plausible. We may live in a universe where the true stable form of matter hides in stellar corpses.
Metallic oxygen at ultra-high pressures. For decades, scientists tried turning breathable oxygen into metal. In 1998, claims at 96 GPa were disputed. In 2022, Edinburgh's Philip Dalliday Simpson and Eugene Gregorians confirmed it. At 96 GPa, or 960,000 atmospheres, pale blue solid oxygen turns dark red metallic conductor.
Electron orbitals overlap, creating delocalized electrons. Resistance drops. Light reflects like polished metal. X-ray diffraction shows monoclinic structure. Conductivity around 100,000 Siemens per meter, semiconductor-like, rising with pressure.
In Uranus and Neptune, at 20,000 plus kilometer depths, 200 to 600 GPa, ices dissociate. Oxygen forms metallic layers. This explains their bizarre, tilted, up to 60 degrees, multipolar magnetic fields, chaotic convection in conducting fluids. Oxygen, vital for life, exists in alien metallic form inside ice giants. Any sample would explosively revert to gas on Earth in microseconds.
Time crystals in extreme gravitational fields. In 2012, Frank Wilczek proposed structures repeating in time without energy input, time crystals, seemingly violating thermodynamics. Most physicists thought impossible. 2015 proofs claimed no equilibrium versions. In 2016, Norman Yau reformulated discrete time crystals in driven systems. Labs, Maryland Ions and Harvard NV centers created them, oscillating at half the drive frequency, broken time translation symmetry. Near black holes, extreme gravity, tidal forces, frame dragging, might form them naturally in accretion disks where space and time interchange. This could explain quasi-periodic X-ray oscillations, 0.1 to 1,000 Hz, stable over decades, in systems like GRS 1915 plus 105 and Cygnus X1, beyond orbital models. Black holes may crystallize time itself, creating perpetual quantum oscillations powered by space-time curvature. Superfluid dark matter. In 1933, Fritz Zwicky saw galaxies in coma moving too fast. Clusters should fly apart without 400 times more mass. Ignored for decades. In the 1970s, Vera Rubin's rotation curves showed edge stars orbit as fast as central ones, contradicting Newtonian gravity. Dark matter, another 27% of the universe, holds galaxies via gravity alone. In 2015, Justin Corey proposed dark matter as superfluid, Bose-Einstein condensate in cold galactic halos, zero-viscosity quantum fluid producing emergent MOND-like force at low accelerations. NGC 1052-DF2, 2018 discovery, has almost no dark matter, velocity dispersion 10 kilometers per second versus predicted 200. Superfluids can be splashed out in collisions. Bullet cluster, high-speed pass-through fits too. Galaxies float in invisible quantum oceans, coherent states of trillions upon trillions of particles acting as one.
Excitonium in white dwarf cores. Excitonium, electrons bound to electron holes, excitons, condensing into superfluid insulator. Lab confirmed 2017, Illinois, others. Excitons usually annihilate in trillionths of a second. Cold, dense enough, they persist.
Gaia 2019 data on 100,000 plus white dwarfs shows cooling pileup at about 15,000 K. They linger about 8 billion years longer than models predict. Explanation: at critical densities, millions of grams per cubic centimeter, carbon-oxygen cores undergo excitonium transition, releasing latent heat, 100,000 decades of ergs, sun's output over millions of years, halting cooling, may trigger sub-Chandrasekhar supernovae. Dead stars crystallize quantum states billions of years before labs caught up.
Topological insulators in magnetar crusts. On December 27, 2004, SGR 180620, a magnetar 50,000 light-years away, unleashed 10 to the 46th ergs in 0.1 seconds, more than Sun's output in 250,000 years, ionizing Earth's atmosphere and saturating detectors, followed by a 400-second pulsating tail at 7.5-second rotation.
Magnetars are neutron stars with 10 to the 15th Gauss fields, quadrillion times Earth's, warping quantum electrodynamics, creating vacuum electron-positron pairs. How do 10-kilometer remnants maintain this without fuel?
In 2018, Matthew Kaplan proposed topological insulators, 2007 discovery, 2016 Nobel. Bulk insulators but perfect surface conductors, electrons unidirectional, topology protected against defects. In magnetar crusts, nuclear pasta, spaghetti, lasagna, bucatini phases at extreme density and magnetic fields, topological transitions create dissipation-free surface currents, maintaining fields indefinitely. Stress triggers sudden rearrangements, releasing stored energy in giant flares. Quantum topology powers the cosmos's most violent engines. The universe doesn't just contain strange matter, it casually manufactures states we chase in labs, revealing how little we truly understand about reality's building blocks. What other impossibilities await discovery out there?